26F. Find the area under the student's curve with the 5 degrees of freedom to the right of 2.2. So go to A105. Okay, degrees of freedom, 5. So we go to row 5 on A105. And I want the area to the right of 2.02. What is it going to be? Okay, so 2.02 is 5%. Do you guys see that? What does that mean? So my t-score is 2.02. Why is it not a z-score? My sample is very small. How big is my sample? 6. Okay. If your sample is smaller than 26, then you do a t-score, not a z-score. How do I know my sample is 6? My degrees of freedom is 5. So if my degrees of freedom is 5, yeah, there's video. You watch the video. Nope, there's not a video. You do need to read. Okay. So in this case, I have 6 draws. So my DF is 5. And I go to 5 on the table, and I go across until I find 2.02, and it says 5%. What does that mean? On my normal curve, but this is not a normal curve. This is the student curve, the T curve. So this is 0. And if I go out to 2.02, how much area is in that tail? 5%. That's what it's telling me. Now, interestingly enough, what if my degrees of freedom were 6? Then 5% would be 1.94. You see that? Okay, if my degrees of freedom were 7, it would be 1.89. What if I had 500 draws? What would the 5% mark be? Well, it wouldn't be degrees of freedom. What is the z-score for a right tail of 5%? We talked about this a lot. 1.66, right? So look at 5%. It starts at 6.3, and as you go down the chart, it gets closer to 1.66. Okay, so this is what it means. Let's say I had 500 draws. Okay, here's 0, and here is plus 2. Nope, sorry, that's not what I wanted. Yeah, this is a normal curve. If this is 5%, then what is this mark right here? Plus 1.66 SEs, right? Whether it's an SEN or an SEP or an SE average, it's 1.66, okay? But I'm only allowed to use the Z table when I have a lot of draws, okay? So what does the T table tell me? Well, it says in this same picture, so this is a T table, 0, 5%. Where is this line? It depends on how many draws you have. Right. So it's just the number of draws minus 1. It'd be 4. Right. It's really yeah, I've never figured out why they don't just use the regular number, like 6 draws. Well, I don't know why they do 6 minus 1, but whatever. Not a big deal. So if I have 2 draws, then my degrees of freedom would be 1. And where is this mark? Look at your chart. T equals 6.31. That's huge, right? That means 5%. If you only take two draws, so let's say you want to find the average height of people in at Emory High, and you go out and you talk to two people, how accurate is your information going to be? Not very accurate. So your null hypothesis would require that your sample be 6.31 SEs away from the average, right? So is taking two samples very good? No, but sometimes that's all you have. Okay? What if you take three samples? That would be 2 degrees of freedom, and t equals 2.92. Wow. So the difference between two draws and three draws is huge. Okay? What about four? So 2.35. Okay, let's jump up. Let's do 10, which would be 9, 1.83. Okay, now let's jump to 20, which is 19, 1.73, and 26, which is 25, 1.71. What's happening? It's shrinking, and it's getting closer and closer to 1.66. Do you guys see that? I'm not sure. 1.71 is not very far from 1.66. So when I print my table, I'll go out to, how many rows are there on that one? I'll I'll try to go out to maybe 50 or 75 or something. But eventually we stop caring about degrees of freedom. Right. Eventually, this number gets so close to 1.66, we quit caring. Will we ever hit 1.66? No. But at some point, we stop caring. Where is that point? I don't know. 100. Well, okay, so Colton has a really interesting idea. Look at 2020. 20 is 1.72, and 21 is 1.72, and 23 is 1.72. So we had three 1.72s in a row. And see, 73 was twice. So two 73s, three 72s. Does that mean there will be four 71s? Something like that. Yeah, yeah. So we might have five 1.71s and 10 1.70s, but it's going to get harder and harder to get close. Right. It's like an exponential decay problem. We'll never actually reach 1.66, but eventually we get so close that we'll quit. Right, exactly. So if you look at the Z chart, will we ever get to 1? No. But eventually we get so close we quit caring. When do we quit caring? At 5 SDs. Okay? So the T table, the whole purpose for the T table is to allow you to do confidence with small draws, a small number of draws. Because otherwise, if we assume that a small number of draws creates a normal curve, then we are going to promote, we are going to say that something is more accurate than it actually is. And we did that yesterday, right? That problem that was in the book, we did it the old way, and we rejected the null. And then we did it using the T table, and we accepted the null. Well, usually that's what you want to do. So what we did yesterday, there was a problem in the book, and so the whole point of the thing was to land inside there, right? So we did a z-score, and the z-score put us way over here. And so we said, reject the null. right? But we only had like 6 draws or something like that. So we threw out the z-score and we created a t-score, and the t-score actually landed us right here, in which case, or sorry, this was, yeah, in which case we accept the null. Does that make sense? Now, what does the t-score really do? It makes your SD larger, and it makes it harder to land in that 5% range, which makes sense because if you don't have very many draws, then you're not very sure. Okay, so that's the whole purpose behind this. All right, so letter B in number 1, the area to the left of negative 2.02. It's going to be exactly the same as the area to the right of 2.02. So the t-table is one-tailed, which is different than the z-table. The z-table is two-tailed, right? Okay. So what is the area between negative 2.02 and 2.02? It's got to be 90. How come? You have 5 in each tail, which would leave 90 in the middle. And to the left of 2.02, 95. Okay, is everybody all right with that? Number 1, the area to the right of 4.02 under the student curve with 2 degrees of freedom is, so we go to 2 degrees of freedom, and the area to the right of 4.02. Is 4.02 one of the numbers in the t-table? No. But 4.02 is going to land between 2, 1 and 5. Shouldn't it be 2.5 and 5? Oh, I see. so the so we would say between 2.5 and 5, right? Because it's between 2.92 and 4.3, but that's not one of our options. Okay. All right, true or false, and explain. To make a t-test with 4 measurements, use student's curve with 4 degrees of freedom. False, you would use 3. And honestly, I have no idea why they do that. Because couldn't you just take the t-table and slide all the numbers down 1? Or up 1, I mean, and then, I don't know. And maybe what they're saying is, if you take 1 sample, then you can't do a t-test. Why can't you do a t-test with 1 sample? Because you have an SD of 0, right? You don't really have an average. You don't really have an SD. So you have to take at least 2. Okay. Yeah. And now so that's a good point. I've been telling you, make more draws. Well, sometimes we can't, right? Sometimes it's really expensive, really expensive. So if you have a small number of draws, you can still do a test. All right. 4. We're just doing A and B in number 4. So the data sets, assume the Gauss model with errors following the normal curve, however bias might be present. In each case, make a t-test to see whether the instrument is properly calibrated or not. What's our expected average? 70. We got that from the chapter. So we expect 70, and this is similar to the example in the chapter. Okay. So for A, 71, 68, and 79, what is the average of the sample? What did you get? Here, I'll just put them in my stat. So these are, for those of you who weren't here, these are calibration tests for a CO2 machine. And they have a prepared sample that's 70 parts per million, and they put it in the machine, and the machine reads it and spits out a number of how much CO2 is in there. And we're just making sure the machine is working properly. So I'm going to clear this out. 71, 68, and 79. And then I do my one variable stats. and I get an X bar of 72.66, and I get a standard deviation of 4.64. Okay, what is my null hypothesis? So the null says it equals 70, and the alternative is going to be, greater than 70. Now, can I do a z-score? No, I can't do a z-score. How come? I have 3 draws. So can 3 points create a normal curve? No. So I need to do a t-score. Now a t-score is a little bit different. For a t-score, first you have to create what's called the SD plus. Okay? And then once you have the SD plus, we're going to create an SE. Which SE are we going to make? SE average, because we want the average to be 70. Okay? The SD plus, and I don't have that up on the wall yet, but the SD plus is simply the SD times the square root of the draws divided by the draws minus 1. So I'm going to take 4.64 and I multiply that by the square root of 3 over 2. I have 3 elements in my sample, so 3 divided by 2. Now, what is the purpose of this? It's going to make my SD bigger. Okay, I don't have very many draws, so do I think that my SD is very accurate? No, I don't. So what I need to do is inflate my SD to cover chance variation. Okay, so I inflate it according to the number of draws. What if I had a lot of draws, like 1,000,000? What is 1,000,000 divided by 1,000,000 minus 1? It's really close to 1, right? So if I take the square root of 3, right. So if I do the square root of 3 divided by 2 and push enter, how much bigger am I going to make my SD? 22%, right? What if I had 20 draws? So it'd be 20 divided by 19. Now I make my SD 2.5% bigger. Okay, what if I had 100 draws? Then I'm going to be making it 0.5% bigger. Is there any point in inflating my SD by 0.5%? No. And the further I go, the closer I get to 1. So when I have 600 draws, I would inflate it by such a small number that we don't care, so we don't do it. Right. So this trick is only needed when your draws are small. And the smaller your draws, the more inflation your SD gets. Okay, so I'm going to take 4.64 and multiply it by the square root of 3/2. And my SD plus, why is it called SD plus? Because I made it bigger. My SD plus is now 5.68. And the reason I did that is I don't trust my SD. Why don't I trust my SD? Because I only had 3 draws. So do you guys understand the concept behind why we need an SD plus? Okay. Now I use my SD plus to create an SE average. So I'm going to divide this by, how do we create an SD average? Divided by the square root of 3. So this divided by the square root of 3. Okay. And that gives me 3.28. Now what do I do? Now I need to create a t-score. So this is right here. 72.66. What's the distance? 2.66. So I take 2.66 and I divide it by 3.28, and I get a t-score of 0.81. If this was a z-score, then we would shade norm and we'd get an area and we would accept or reject the null. Did I land in that 5% window on the right? No, because the cutoff is 1.66. So if this was a z-score, we would accept the null. Okay? But we're not doing a z-score, we're doing a t-score. So I have to go to A105. A105, degrees of freedom would be 2. So degrees of freedom 2, and I need to find 0.81, which is 25%, really close to 25%. Okay? Do we accept the null or reject the null? We accept the null, right? So always remember, this is the alternative, and this is the null every time. Right. Did we land in the same window that 70 is in? Yes. So we accept the null. So what we say is the numbers that came out of the machine are not significantly different than 70. Right? Is the machine working? We think so. We think it's working. We don't need to change anything. Okay? So now let's redo the calculations, but we're going to use a larger sample. So I'm going to go in 71, 68, 69, and then 84. Read those off for me. Okay. Now I will redo. I'll redo these, and I get an X bar of 76.28. So 76.28, and I get an SD of 6.5. So now I need to create my SD plus. How do I create my SD plus? 6.5 times the square root of 1, 2, 3, 4, 5, 6, 7. 7 over 6. Is this SD going to grow at the same rate that my last one did? No, because 7 over 6 is smaller than 3 over 2. So I take my SD, 6.5, and I multiply it by the square root of 7/6. And my SD plus is 7.02. Now how do I create my SE average? Divide this by the square root of 7. And I get 2.65. That's my SE. Now what? I need to create my t-score. So this number is now, this number is 76.28. So the difference is 6.28. 6.28 divided by my t-score, or sorry, my SE, and I get 2.36. So T is 2.36. Now stop. If this was a z-score, would I accept or reject the null? I would reject, because I'm further to the right than 1.66. Okay? But we're not using a z-table, we're using a t-table. So go to A105. Degrees of freedom is 6. And I need to find 2.36. Where is 2.36? 2.36 is between 5 and 2.5. So it would probably be about 2.7, somewhere in there. So we have just decided that this area is somewhere between 2.5 and 5. Do we accept the null or reject the null? So this is the 5% mark right here. We landed right there, which means we reject the null and we say the values that came out are significantly different than 70. Are they highly significant? No, they're not within 1%. Okay, so let me draw this again. 0. Okay. The t-table with 6 degrees of freedom says the cutoff for, hold on, the cutoff for 5% is 1 point, so t equals, no, it's on 1.95. Look at, for 1.94. Okay. And the cutoff for 2.5% is t equals 2.45. And just to show you, the cutoff for 1% is 3.14. These are t values. Okay? If you are to the right 1.94 SEs, that means there is 5% to the right of 1.94 with 6 degrees of freedom. Okay? Our t-score was 2.3 something, whatever, doesn't matter. Okay? Where does 2.3 fit? Right here. Right? Well, we are testing significance. So this is the null, equals 70. Anything to the right of this is the alternative. Does that make sense? So this is saying, this stuff in here, the machine works. It doesn't need to be calibrated. Okay, but if you land anywhere from here over, you have to calibrate the machine. You'll have to turn it down a little bit. Okay, so the first time we did it with 3 values, we landed like right here. And we said, nope, it works just fine. Don't mess with it. But then we did more tests, and then we landed right here, which is outside the range of the null. So we reject the null, and we say the values that the machine is spitting out is significantly different than 70. So we reject the null, and we accept the alternate. Does that make sense? Okay. All right. Next one. A new spectrometer is being calibrated. It's not clear whether the arrows follow the normal curve or even whether the Gauss model applies. In 2 cases, the assumption should be rejected. Which 2 and why? The numbers are replicate measurements on span gas. So we're just going to do, we'll just do 1 and then see whether we reject or not. Okay, did C? I think it's A. Right, so we're just going to do A. We'll do A and see whether it's reject or accept. Instead of doing all 3, we'll just do 1. Okay. All right. Read off the numbers for me on A. Oh, slow down. 71 and 70. 72. 71. 8. Okay. So 1 variable stats. maybe. Trying. There we go. All right, so I get an X bar of 71.58, and my N is 12. That's kind of nice, right? It counted them for me, and my SD is going to be 7.33. So I want it to read 70, and we ended up with 71.58. So first I need to say my null equals 70, my alternate is greater than 70. Now I need to compute my SD plus. So I'm going to take 7.33 times the square root of 12/11ths. So 7.33 times square root of 12/11ths. And this will make it a little bit bigger, not a lot bigger. So my SD plus is 7.66. Now I need an SE, average. So I take 7.66 divided by the square root of 12, and I get 2.21. Now what? I need a t-score, so what's the distance from 70 to 71.58? So 1.58 divided by my, whoa, that was weird. It's 1.58 divided by 2.21, right? Okay, 7.15. So I get a t-score of 7.15. Now I need a p-value. A p-value is the area. So I go to A105. And how many degrees of freedom do I have? 11. So the area to the right of I wrote that wrong, sorry. Of 0.715, I really messed that up, whatever, is going to be between what? It's going to be between 10 and 25, right? So do I accept the null or reject the null? I accept the null because my p-value is bigger than 5. So the area to the right of 0.7 is more than 5%. So is the machine working? Yes. In that one, the machine is working. And then, so in B and C, it says they're not. Okay. And then we need to do 6 and 7. A long series of measurements on a check weight averages out to be 253 above 253 micrograms above 10 grams, and the SD is 7. The Gauss model is believed to apply with negligible bias. So the Gauss model means instead of looking at the average, you just look at the difference, right? So instead of saying 10.253 grams, we're just going to say 0.253. Does that make sense? So instead of saying I am 67 inches tall, I would say I am 3 inches lower than the average. That's what the Gaussian model means. Instead of talking about the actual value, you just talk about how far away it is from the average. Okay, 10 measurements. At this point, the balance has to be rebuilt, which may introduce bias as well as changing the SD of the error box. 10 measurements on the check weight using the rebuilt scale show an average of 245 micrograms above 10 grams with an SD of 9. Has bias been introduced, or is this chance variation? So what do we expect the average to be? 253. So we expect 253. Okay, and we ended up with 245. Which SD am I going to use? Am I going to use the 7 or the 9? Well, does the 7 apply anymore? No, the scale's been rebuilt. Right? They've changed some things. So it's the SD of the sample. I'm hoping. That's my guess. So my SD is 9. I need an SD plus, which would be 9 times the square root of, not 9, it says 10 measurements. So 10 ninths. So 9 times the square root of 10 ninths is 9.49. Okay, now I need an SD or an SE. Which SE am I going to use? This is an average again. So I take 9.49 and I divide it by the square root of 10. And I get 3. Oh, how nice is that? Okay, now I need a t-score. What is my t-score? Well, that would be negative 8. So negative 8 divided by 3 gives me a t-score of negative 2.66. Now I might as well just well, if this was a z-score, we would reject the null for sure. But I might as well just forget about the negative, right? Because the t-score table is right-tailed, so I'm just going to flip the whole thing around and change it to a plus. Okay, we go to A105, and we go to 9 degrees of freedom. What range does 2.66 land in? It's in between 1 and 2.5. So somewhere in between 1 and 2.5. So if the area is between 1 and 2.5, we reject the null and we say the values are significantly different than 253. So we think that there's a new average. The old average was 253, but we had to change some parts on the machine, and when we did that, now the average is lower than it used to be. Okay? Got it? All right, last one, number 7. Several thousand measurements on a check weight average out to 512 micrograms above a kilogram. The SD is 50. Then the weight is cleared. The next 100 measurements average out to be 508 micrograms above 1 kilogram. The SD is 52. Apparently, the weight got 4 micrograms lighter, or is this chance variation? So first off, if you do several thousand measurements, what can you say about 512? It's probably the true average, right? Several thousand. We're just going to trust 512 as the true average. Okay? So 512, 508. And which SD are we going to use? The 50 or the 52? The 52, right? So we have to inflate 52. Oh, do we have to? We have 100 measurements. So do I use the T table or the Z table? Oh, Z table. That's so much nicer. So my SD is 52. Now I create an SE average, which is 52 divided by 10, which is 5.2. Okay. Now, this is a difference of 4. 4 divided by 5.2. It's actually negative 4, sorry. Negative 4 divided by 5.2. And I get a z-score of negative 0.769. Now I shade norm. Shade norm from negative 5 to negative 0.769. And then I get a p-value, and my p-value is 22%. What does that tell me? I accept the null and I say the weight is not significantly lighter than it used to be, right? The question was, did the weight lose some of its mass? No. This is totally explainable by chance error. So the new weight is not significantly less than the original. Kilogram. Mm-hmm. So the box model, we so in the box model we would just put we don't know what's in the box, right? We we know that the average of the box is 512, right? We assume that the average of the box is 512. But what's really in there? A whole bunch of different weights. Well, it's actually just one weight, but anyway. Is that, I mean, does that make sense? Well, yeah. So, yeah, the null equals 512 and the alternate is greater or less than 512. All right.